In our 7th video lecture, we will learn about correlation and regression. Part 1 looks at correlation. Correlation is defined as the relationship between two quantities or variables, such as that when one changes, the other also changes or does not. We want to know that as well. In order to understand when correlational studies would be useful, we have to first return to causation. Remember that with true experiments, also called randomized controlled trials, we use randomization and control groups to establish that A caused B, variable A caused changes in variable B. And that's because randomization and control help to reduce the likelihood that that relationship, A causing B, is caused by a third variable or confounding variable or extraneous variable. Randomization helps with this because when you randomize people into two groups, you minimize the likelihood of just conveniently allocating people into groups and having them be non-representative, meaning one group looks quite different than another group. Control groups help because whenever you have a finding, let's say that A caused B, we also want to know whether if you take away A, does B also change as well? And that gives us more information regarding whether B is changing by itself or whether B is changing just because of variable A. Here's an example of in the past that we've used to articulate when you would use a true experiment. You have an intervention group, which is CBT, compared to a waitlist, that's our control group, for depression scores on the Beck Depression Inventory. However, sometimes we cannot use either randomization or control. Our birth defect study is an example of this. You cannot ethically invite people into a true experiment by telling them that if you participate in this, you will be given a drug that is quite likely, or at least there's a possibility, that is going to give your child a birth defect. That study is difficult to even get through any kind of an IRB, because essentially you're telling your participants, by participating in this study, you are exposing yourself to harm. That there's a great likelihood that you're going to be harmed or a loved one will be harmed by participating. So in a study like this, we cannot really have a true experimental design in order to look at the relationship between the drug and birth defects. So how do we look at that relationship? Well, in such cases, a correlational study would be helpful. We could, for example, look at historical data, known as ex post facto data, and look at whether or not people who naturalistically, meaning by themselves without being asked to, took a drug and whether or not that caused birth defects. And you could look at the rate of birth defects for the people who took the drug compared to people who did not. Now, the downside to those kinds of studies is that we cannot establish that A caused B. In other words, people who took the drug their children or babies had birth defects. And this is because of confounding variables. There are other reasons why people who took that drug may have developed birth defects. That could be things like their response to the drug. It could be their diet. It could be not taking the kinds of vitamins they should have. All of these other variables. So regression, as we'll see later, helps with this. It reduces the impact of confounding. But without regression, without looking at multiple variables, when we're just looking at two variables with something like correlation, we can't necessarily claim that there is causation occurring between variable A and B. Here's a fun graphical representation of why correlation does not imply causation. You have a boy here and a girl, two children and a mother. There's a TV remote that's through the TV screen, and the boy says correlation does not imply causation. The mother is assuming, because the boy is not holding his remote anymore and the girl is, that the remote was put through the TV screen by the boy. However, it's just as possible that the girl, who has kind of a sly smile there in the background, could have also have put the remote through the TV screen. We don't know that, but That's the possibility that could occur when we have a correlational study, that there are these third variables that could impact the result. So how do we understand correlation? What is the correlation about? Well, correlation is determined by what are called fit lines on graphs that show whether a relationship exists between variable A and variable B. The fit lines on the graph in front of you are apparent by looking at the red line and the green line. Those are both fit lines. You'll notice the middle figure, if you will, the middle graph, does not have a line. That's because it has zero correlation and therefore zero fit line. So let's look at positive correlations first. Positive correlations occur when the value in variable B, known as the dependent variable, increases as the value in variable A, the independent variable, increases. So looking at auto insurance cost for positive correlation, that green line, it looks like as more auto accidents occur, a person's auto insurance cost increases. Negative correlations occur when the value in variable B, the dependent variable, decreases as the value in variable A, the independent variable, increases. So looking at the red line, as auto mileage increases, the value of the car decreases. The value of correlations is 0 to +1 for positive correlations, or 0 to -1 for negative correlations. And just going back to our prior example, I did not cover, but it might be helpful to go back and look, that a non-existent or zero correlation occurs when you have, for example, the body color of the car body color, and the quality of the car. There's presumed to be no correlation there. And when you have no correlation, you have what's called a zero correlation. A positive correlation is 0 to +1, negative 0 to -1. Let's look at the graphs in front of us to understand this. So at the top left you have r equals -0.9. And you'll notice that the line is strongly clustered together, that there is a clear line there, and that as one increases, the other decreases, known as a negative correlation. The line becomes less defined slightly to the right, the r equals -0.5. There is still a line going on. You can see there's a fit line in there somewhere. But the points, the data points, are not clustered so closely together. And then to the right of that we have r equals 0. And this is where you have really no relationship. There's no line. All of the dots are scattered around. Bottom left you have r equals 0.5. This is a positive correlation. As one increases, the other increases. The dots are not quite as clustered as closely together as you'll see next, which is r equals 0.9. Those dots are clustered much closer together and approximate a much closer fit line. Even closer together is slightly to the right, which is r equals 1.0. And you'll see there the dots are they are perfectly in a line together, and you see no variation in terms of what the line looks like. So in other words, the more variation between the dots in relationship to the line, the less strong the correlation is. Correlations closer to +1 or -1 are thus stronger than correlations closer to 0. So what do the numbers mean? Well, in order to determine the effect size of a correlation, we need the following guidelines, and R, by the way, is an effect size. A small effect is 0.10 or -0.10, 0.1 or -0.1. Medium is 0.3 or -0.3, and large is 0.5 or -0.5. With correlation, it is vitally important to visually inspect correlation graphs and not just interpret the Pearson product moment statistic known as R. This is because the same correlation value can look very different. The four graphs that you see in front of you have the same R value, but you look at the data points and they are quite different graphs. And so we need to understand the graph as we are interpreting the R value. Notice that the graphic on the top right does not have what we might call a linear line. In other words, the line has a curve to it. It doesn't completely follow the same straight line. We would use regression to more adequately understand how that line twists and turns and changes over time. Correlation doesn't really help us with that. It only helps us in the case where we have more straight lines. Here are some further fun examples of correlation. A strong positive relationship might be found when you have more household units in terms of foreclosures. So the more household units you have, the greater the foreclosure rate is going to be. There might be a strong negative relationship if you look at the percentage of people who are college educated in a town, say, if you look at different towns, and the unemployment rate in those towns. So the more people in the town who are college educated, the greater the percentage, the lesser the unemployment rate, or so the theory goes, according to this graphic. Then we would find no relationship, or very minimal relationship, if we were looking at the number of pet owners among people who are college educated or not. So the percentage of people college educated and whether or not they were pet owners. I don't necessarily see a relationship there, and so there may be no relationship at all. Okay, here are some other fun examples that were taken from actual research studies to explain to you how correlation graphs can be useful, though we always wonder about the impact of third variables when we are looking at correlation. This image was originally published on the National Institutes of Health website. It looks at a 20-year lag time between smoking and lung cancer. You look at the bottom, the x-axis, we have year 1900, 1920, 40, 60 and 80. We have cigarettes smoked per person per year. And then we have lung cancer deaths per 100,000 people, looking at men specifically. So you'll notice, looking at the green line, that the more cigarettes smoked per person per year, there seems to be kind of an increase over time in terms of the year. And if you look at lung cancer rates among men, there's also an increase over time over the years that looks almost similarly, except there's a 20-year lag time. And that's kind of interesting data that may be part of the reason why people develop lung cancer is because of their amount of cigarettes that they are smoking 20 years earlier. But while we can maybe infer this from the graph, there are other variables that may explain this. For example, we don't know about the overall health of the men, how old they were when they developed lung cancer, whether or not they stopped smoking at a particular age. So we kind of wonder about that. There are all these other variables that could impact this graph. Here's another example. Does autodependency make us fat? This is a really fun graph. It shows us how obesity falls sharply with increased walking, cycling and transit use between different countries. So if you look on the x-axis, it has this series of countries, and the red line is the percentage of people who are obese, and the green line is the percentage of people who use walking, biking, transit, I guess on a daily basis. So what you notice there is that as if you look as the countries kind of among the countries, the more people who are walking, biking, using transit, the lower the obesity rates compared to other countries. This is data that was presented from Rutgers University urban planning professor John Pucher. Now, there are other confounding variables that could be present here, the most apparent being, of course, diet. We wonder about what kinds of calorie intake people are having in those various countries, if that's different, the kinds of foods that they're eating, if they're high in fat or not, high in carbohydrates or whatever. And so that could impact this data. This one's a bit more controversial. It's kind of goofy and fun. I can't believe they actually put together this graph, but you find all kinds of interesting things on the internet. This is taken from 2006. I guess this is relative to the 2004 election. And they found that in states George W. Bush's share of the vote closely correlates with white fertility, meaning babies per white woman. The more babies that a white woman has, the larger Bush's share of the vote. Now, there are all kinds of confounding variables again that could be present here, such as regional location, someone's political leanings, or even their religious values, all kinds of different things going on that could explain some of these numbers. So, in addition to third variables, there are other problems with correlation that I need to tell you about. The biggest one is directionality. And this is when we don't really know if variable A caused change in variable B, or vice versa, that variable B actually causes change in variable A. Here's a fun example of this, looking at two penguins talking. The dialogue reads, "Do you think all these film crews brought on global warming, or did global warming bring on all these film crews?" The idea is that we can assume that the film crews are here because of global warming, but in fact we can't really substantiate that relationship with statistics. We don't really know who is causing what in terms of that relationship. Here's an example of a correlation table that you often find when you are reading through a research article that has correlational statistics in it. This is taken from an article about parents of adoptive children and looking at correlations of co-parenting, division of labor, and child behavioral adjustment. You'll notice here, if you look at the variables, those are the most left column. Variables 7 and 8 are variables that look at child behavior. 7 looks at child behavior for parent report, and 8 looks at child behavior for teacher report. If you choose another variable, let's say we're interested in whether supportive parenting has a prediction on child behavior, so that's variable number 1. So if you look at the column slightly to the right of the list of variables, so the column that says number 1, you follow that all the way down to number 7, and you look at what that number is. It's minus 0.22, and there seems to be, in other words, a small negative correlation between supportive parenting and child behavior adjustment, meaning the more supportive you are as a parent, the less a child is going to have negative behaviors according to parent reports. So we can glean some important information here, but just remember that there's still the impact of confounding variables when you're reading through correlation tables. We've looked at correlation. Part 2 is now going to look at regression. Regression helps us with a variety of things, including the impact of multiple independent variables on the dependent variable. So, regression is similar to correlation, except that it can predict values of the dependent variable based on the independent variable. This is useful for the purpose of probability. And remember that most statistics is really grounded in probability, which explains why correlation is one of the most popular statistical tests used in research studies nowadays. It can also examine non-linear relationships, especially looking at the trajectory of change. This is very useful, particularly in counseling studies, because people don't tend to change in a completely linear fashion, step over step over step. They tend to get better either slowly at first or faster at first and eventually reach plateaus, and so knowing all of that information is useful. It's also, as I mentioned earlier, useful to examine multiple IV, or independent variable, correlations on the dependent variable. This is known as multiple regression. So, in terms of prediction, regression is helpful for predicting values of the dependent variable based on the independent variable, known as probability. The graphic here looks at BMI being used to predict fat percentage. And in other words, we look at, as BMI increases, it looks like percentage of fat is also increasing, and that's a positive correlation. Now, you'll notice the curve, though, is not completely linear. There's kind of a curve to the curve. And so, because it's not a completely straight line, we use regression to understand what that line means in terms of, as BMI seems to be increasing, there's a plateau effect that's going to occur eventually, whereby the percentage of body fat is not going to keep increasing exponentially with BMI. So, in terms of nonlinear relationships, let's look at what this means in terms of a graph. If you look at A, it shows a positive linear correlation, and B looks at a negative linear correlation. Essentially, you're looking at, there's a direction to the line, it seems to be following a fairly close line rather than a curve. However, when you get to C, D, and E, you'll notice that the line changes. It's not a straight line anymore. C is no correlation at all. There's just a big blob in the middle. D, however, is what we would consider curvilinear, meaning it's not a linear line. There's a curve to it. And you can see that it increases sharply and then drops off. It's almost like a half circle. And then you have an inverted half circle next for E, whereby people decline initially and then start increasing. And that's also curvilinear. Now, the correlation, if you look at the R value, is still the same, still 0 for both of those, even though there obviously is a relationship. So R is not particularly useful. Correlation is not useful when you have nonlinear relationships, because the statistic isn't going to be significant, even though there clearly is a line. Here's another example of when you would use regression for nonlinear relationships. We have probability to vote on the left, that goes up as a percentage, and then the 1 through 10, 0 through 10, amount that people like a particular political party. And it shows you that after a while, say you get to about 7 or 8, there isn't a particular impact of liking a party. It kind of plateaus after a while in terms of how likely someone is to vote. So how do we determine regression? Well, regression is based on different kinds of numbers than correlation. Regression looks at the standardized effect for each independent variable and the dependent variable by looking at what's known as the slope line. This is called B in an unstandardized format and beta in a standardized format. You can see there what the slope line is, rise over run, as one increases, the other increases, and we're interested in that relationship. Here's an example of when a model fits data well or does not fit data well in terms of linear relationships. We were just talking about that earlier. If you look on the left, you have a line and there are dots, data points above and below the line. We also find that if you look slightly below that, when there's no correlation, again you have dots up and below the line. However, to the right we see occasions where we really need to be using regression instead of correlation, when the model does not fit the data well. And that's when the dots above and below the line are in an obvious pattern. It's curvilinear. There's kind of the half circle there. And again, if you look below where it says there is no correlation, there actually is a correlation, because dots are obviously in a curvilinear kind of form, and they're obviously following some kind of a curve, and that's when we would be using regression. So in addition to looking at nonlinear relationships, and in addition to look at probabilities, we can also use regression to examine multiple independent variable correlations on the dependent variable, known as multiple regression. So for example, if we were interested in what causes someone to have a higher or lower salary, and looking at the impact of multiple things on that at the same time, for example education and gender and age and competence, we might have a graphic that looks a little like the one to the right of that, which is when you have the y, and that's the dependent variable, and looking at the impact of all of those independent variables, the x variables, x1, x2, x3, x4. And that's useful because when you start combining variables, they start to share variance between one another and help overall to explain a greater percentage of variance for the dependent variable. So in other words, if you just took x1 and took all of the other circles out, you wouldn't have the amount of shaded area you would if you had all 4 of those variables. So in other words, you have a stronger prediction when you add in 4 variables to one variable in terms of explaining what causes a person to have a higher salary than someone else. In multiple regression, multiple independent variables can be combined to create a more powerful prediction. Another example from the counseling literature is when we look at client outcome and look at the predictions based on things like therapeutic alliance or relationship, client expectancy of change occurring, and therapist allegiance to the model being provided, the technique or theory. When we combine all of these, we have a more powerful prediction for whether or not therapy is going to be successful than if we just took therapeutic alliance, for example. Now, we might also expect that expectancy and allegiance and alliance are all going to correlate together a little bit in addition to correlating with outcome. And thus, regression is helpful for explaining the interrelationships in addition to the overall impact of the relationship. So we compare these IVs to determine whether one of them has the most impact on the dependent variable and whether there are additive effects for adding other variables in terms of explaining why someone is going to get better or not in terms of outcome. Here's a further graphic for that. I'm just going to continue repeating graphics to help reinforce this idea. So here we have variance in the dependent variable explained by independent variables. dv is that yellow circle. We have 2 independent variables, the blue and the red. It shows the green area, blue and yellow equals green. The green area is the variance in the dependent variable that is uniquely explained just by IV1. Okay? Whereas the orange, that's red plus yellow, is the variance uniquely explained by IV2. Okay, useful. And we also have the brown area there, which is in the middle, and that's explained by both IV1 and IV2. Now, if you add IV1 and IV2, you have a much greater shaded area compared to just having, say, IV1. Another example of this. You have your dependent variable, that's the circle that's not shaded, and then you have some dependent variables. You have the first variable, which is one overlap with one variable. You see that in terms of the one on the top, the lightly shaded. Then you add a second and you have the impact of 2 variables, and then if you have a third, you have the impact of 3 variables. Here are some examples of when regression can be useful for not only looking at the impact of multiple variables on the central relationship, the dependent variable, but also those interrelationships. So you'll notice case 1 shows that relationship with, if you look at x as being, if you look at y as being the dependent variable, there's a obvious relationship with x1 on y, but there's also an impact of x2 on x1, not necessarily on the dependent variable, that's y, but on the independent variable. So we would want to know, for example, the relationship of, let's say we were looking at CBT on depression, and then we added in something like the relationship. Maybe the relationship has no impact on depression, but has quite a large relationship on whether or not a therapist is likely to use CBT, for example, or whether or not a client is likely to stay in CBT, those kinds of things. Case 2, you have y, and then you have x1 and x2, and you'll notice that x1 plus x2 results in a larger shaded area of y, the dependent variable. And there's also a commonality between x1 and x2, that's the shaded area in pink. Case 3 is when you have no interrelationship at all, so both x1 and x2, the independent variables, have an impact on y that's additive. They have different sources of variance on y, but there's no interrelationship there. x1 and x2 do not share data, they do not share variance, if you will. And then case 4 is the most complex, and that's when you have y, or the dependent variable, and then you have x1, the first independent variable that has an impact, and then x2, the second independent variable that has an impact, but also has a large shared variance with x1. You also notice in this graphic that if you took out x2, you wouldn't lose anything in terms of explaining variance in y, because x2 just covers the same shaded area in y as x1 does, if that makes sense. Here's another silly example of how regression works with chocolate chip cookies. You have all these variables in a chocolate chip cookie: vanilla, eggs, flour, milk, chocolate chips, and you could look at, for example, how those elements combine with the flour to make the cookie. So, for example, maybe chocolate chips is less important in terms of combining with the flour, maybe the same with vanilla, but milk and eggs is very important. But maybe chocolate chips also has some interrelationship with milk. It's just a weird, strange example, but it helps you understand what regression is about in terms of explaining those interrelationships and whether or not a cookie is going to be effective, how the flour is combining. Whether it's going to be tasty, I guess, more than effective. Okay, so when is multiple regression useful? So you do have occasions with correlational graphs where you'll have an impact of a third variable, and if you don't look at the impact of the third variable, you'll have odd results, weird correlation graphs. Here's an example. The real cause of increasing autism prevalence, they have autism increasing year over year, and organic food sales increasing year over year, and the relationship between those two is very strong, R equals 0.99. So what's going on there? Does it seem like organic food sales is causing people to develop autism? Well, there's obviously going to be some kind of third variable there, and maybe that's that organic food sales is increasing because the other available foods are all being laden with GMOs, and the GMOs are causing autism. Or it could even be something completely unrelated to that, which is that just, I don't know, people are becoming more aware of holistic kinds of approaches to things, and that's just occurring by chance with this increase in autism prevalence. So multiple regression is useful because we would start looking at various impacts of different independent variables on things like autism prevalence, and it helps us to understand whether something really has a relationship or not. Although it cannot determine causation because it doesn't have enough control, there's no control groups, regression does help us reduce the chance that any relationships may have occurred by chance or by confounding variables. And that's because when you are looking at multiple independent variables in terms of their impact on the dependent variable, there's a greater likelihood that you're going to find some degree of explanation in terms of what is confounding the results. Here are some examples of different kinds of regression lines, and these are straight lines, so these are not non-linear lines, if that makes sense, or curvilinear. These are all linear lines. First we have fixed intercept, fixed slope. So in other words, same intercept, same slope. Next we have random intercepts, fixed slope. So you have multiple people here who have different intercepts. They cross the y-axis at different times. They have different levels of something initially compared to other people. But the slope is the same. The level of growth is the same. Next you have random intercepts, random slopes, which is when people have different quantities of something when they begin a study at 0. But also the slope lines are different as things, as the study continues, as time goes on. Then we have random intercepts, random slopes, and this time we have a negative relationship rather than a positive relationship between intercepts and slopes, meaning that in C we see that basically the slope lines are increasing based on the intercept, whereas you see that in D the slope line is decreasing based on the intercept. E is about random intercepts, random slopes. So the example here is that there's no relationship between intercepts and slopes. It's random. And then F is random intercepts, random slopes. And there's a positive relationship between intercepts and slopes here with no fixed slope. Instead of Pearson's R, regression uses R squared as the test statistic, and basically this is just R times R. This is the percentage of variance accounted for by the combination of predictor variables. So here's some practice looking again at parents of adoptive children, that article. You have in this table both B, which is in italics. This is basically the unstandardized regression coefficient. You have standard error for B, and then you have beta next to it, and then T. Beta is most commonly used and interpreted because it is standardized, meaning those units make more sense. It's almost like looking at the difference between standard deviation and variance. Variance is very hard to interpret by itself because the numbers can't really be compared between studies, whereas standard deviation is useful because it has standard units, and beta is the same way. R squared is also reported here, as well as F, so looking at the difference between various variables. So we have beta slopes for supportive, competition, and dissatisfaction in terms of externalizing problems, meaning that if parents are more supportive, the child is less likely to have externalizing problems, whereas if a parent is more competitive, if the parents in between each other are more competitive, the child is more likely to have externalizing problems. And if there's dissatisfaction in childcare divisions between parents, the child is also more likely to have externalizing problems. That I interpreted that just by looking at the beta slope line. Then we have R squared, and R squared is interpreted as being 0.13, which has specific parameters in terms of the size of the effect, and it's going to be smaller than R is because it's R times R, which is going to be a smaller number, and so it's going to be a fairly large effect, and you can look at your effect size table to interpret that. So we have just learned about correlation and regression. That concludes this video lecture.